Yeah, welcome to lecture number 4, an introduction to Lattice Boltzmann in winter 2025. So today we'll come to the actual discretization. So we'll talk about our first Lattice Boltzmann model, which, because we start in one dimension, will not yet be necessarily very useful, but it's important to get things to understanding. So mathematicians always start with 1D. And in fluid dynamics, if you cannot understand fluid dynamics in 1D, and actually you cannot understand fluid dynamics in 2D either. Yeah. But anyway, we start from one dimension and then we go up the dimensions. We are visible, yes. So last time we ended more or less with the Navier-Stokes equation, and the reason for deriving this, I mean, this is the equation that we want to solve, but we wanted to see how far we have to go with the approximation of the Boltzmann equation in order, or the BGK equation, the BGK approximation to the Boltzmann equation, in order to get the Navier-Stokes equation out of it. Okay, in a little bit different format than last time. Yeah, I'll now use this row here with an asterisk. In a minute I'll explain what I mean. So there is a time derivative of u and u dot nabla u. So this is the advection thing, and on the other, by convention, we write this on the left-hand side, and by convention we write the other thing on the right-hand side, which is the fluxes. So there is we've seen this kind of flux, the gradient of something that we can identify with the pressure, yeah, which is a density times the speed of sound squared, plus something that we can identify with the diffusion of momentum. So last time, because I mean, I actually said we try to get to the Navier-Stokes equation relatively quickly, so we were not absolutely accurate, and it is not obvious from there on where we get this density in front or inside the operator. Actually, also the tau is in between these operators if you go to really the details. So there's one derivative. I mean, the Laplace operator is a second derivative, and this is actually split up where the inner derivative acts on u, and the outer directs on the viscosity times the derivative of u, right? We don't want to go into this detail. The good thing about Lattice Boltzmann is that actually it places these operators in the right order automatically, in the physically right order. So you don't need to discretize them in a particular way, given that you will have a tau that is not constant, for example, right? So usually, okay, we don't want to bother with this now. But if tau is not a constant, then the operators, because they come from kinetic theory, they are in the right order. And in the Navier-Stokes equation, this is of course not automatically the case. Okay, so we can identify the speed of sound as the Boltzmann constant times the temperature divided by the mass of one particle. And what I mean with this rho asterisk is that we had this particle density, which comes at the unit 1 over cubic meter, and when we multiply this by the mass of one particle, we have the actual mass that you would see in the Navier-Stokes equation, usually. Okay, yes, and then we would like to, we already last time we started saying that this here, this I don't know whether I always have to do it like this. Sorry, technical problems. Already solved. So this here, yeah. So this we identified with the viscosity. This we identified with the viscosity, and we know that this tau, the mean free time, yeah. So the mean free time can also be written as the mean free path divided by the speed of sound, right? Yeah. So this actually this tau cs square actually can also be written as lambda cs. So that would be the same thing. That would be the same thing. And now if you multiply, oh no, don't multiply. If you divide this by a velocity scale and a length scale, then what do we see here? We have the Mach number being U divided by CS, right? And we have the Knudsen number as lambda divided by L. So this is then obviously the Knudsen number divided by the Mach number. If we or it's not consistent. Wait, it's not consistent. I have to write. I always tell the students the left thing and the right thing on the equal sign has to be the same. So sorry, yeah. So this thing here, I mean, you can make the entire equation here. I mean, U and L, these are the scales, so they are kind of constants, yeah, that you can use to make the derivatives here dimensionless, and where all the dimensions remain is here in this part here, where we get something that looks like the Knudsen number divided by the Mach number. And this Knudsen divided by the Mach number we call, or let's put it this way, we have Knudsen, so Knudsen divided by Mach. You see this is this up here obviously is the kinematic viscosity, yeah, divided by U and L, and how, I mean, now you would identify this as what? This is 1 over the Reynolds number, yeah? So because we define the Reynolds number as UL divided by nu, or we can also, I mean, usually in the books you will find it like defined like this, where you have mu, and mu being rho times nu, and this is called the, okay, so this is the two things that we distinguish. We call this here the kinematic viscosity. Please never say kinetic viscosity, yeah, even though it comes from kinetic theory. It's the kinematic viscosity. The kinematic viscosity is the thing that is the proper diffusion coefficient. So all diffusion coefficients, and this is something that I expect you guys to know by heart, that the diffusion coefficient has the unit square meters per second, because it is something that moves for distance, for mean-free path in a thermal velocity. Yeah, so it is length times velocity. Yeah. So, and the other thing here, of course, this mu is the dynamic viscosity. And this is the thing that we measure in, what is it, Pascal times seconds, Pascal seconds, yeah? It is usually useful to, in practice, it is useful to use the dynamic viscosity, because the dynamic viscosity, strangely enough, is the thing that is constant, yeah? While the kinematic is not. Can you give me an idea why this is the case? Okay, well, I write this velocity scale. A little bit mysterious, but actually logical. So how could this be? So is this new to you? No. So you know, though, then explain.
What was the question?
The question was, why do we prefer to have the dynamic viscosity? And when I explained that the dynamic viscosity is the thing that tends more to be constant, especially in compressible flow, than the kinematic viscosity. What's the problem with the kinematic viscosity? Okay, say it's strange to say it's constant. It is independent of density, yeah? Which is strange, because, you see, we multiply here with density, and then I say that this thing here is independent of density. How comes? Nothing to do with gradients. Okay, so you have here nu, yeah? In nu, you either have the way, okay, you can have it in different ways, but in nu you have the mean free path. When you increase the density, so basically it's like this. When you have twice the density, twice as many particles in the same volume, you have half the mean free path, right? So then therefore when you multiply this by density, you get something that is constant. I mean, that is not dependent on density, yeah? While the kinematic viscosity on its own is dependent on density. Okay, so if you're already spending too much time here, we've not even started. A few observations about what we had with the Navier-Stokes equation. Last time already, the Navier-Stokes equation has been derived last week. Actually, am I well audible? Okay. last week we derived the Navier-Stokes equation under the assumptions that the Knudsen number is larger than 0 and that the Knudsen number squared is going to 0. Yeah, so we have a cutoff at Knudsen number square. So meaning that all of this works only for a finite Knudsen number, because otherwise we end up in the Euler equation, which behaves differently from the Navier-Stokes equation. It's small, but it's finite. So it's not going to 0. Now what we are also assuming is that the Reynolds number that we just introduced is fixed. By this, okay, that potentially sounds a little bit strange. So by fixed Reynolds number, I mean that because we now go into discretization, we want our Reynolds number to be independent of the resolution. Yeah? I mean, that may be obvious, but from a historical point of view, it is not obvious. And so suppose you look into the books, for example, by Tim Krüger, yeah. You will find, and also by Mohammed, you will find methods to analyze the Lattice-Boltzmann equation that we are not learning in this lecture here, and which is called the Chapman-Enskog expansion. So maybe when you tell somebody that you went to a lecture of Lattice-Boltzmann, they would assume that you learned about the Chapman-Enskog expansion. And I'm telling you, we are not doing Chapman-Enskog expansion here, but I'm telling you that something like this exists. And very, very briefly, just for the context, the Chapman-Enskog expansion is an expansion technique that was actually is in a sense similar to what we did last time. Yeah, we do a Taylor expansion and go from the kinetic equation to the Navier-Stokes equation. So this is a similar purpose. But this technique is for physical analysis, and it's not developed for the analysis of a numerical scheme. Now, the reality is, because this is the method of choice that has been around before Lattice-Boltzmann was invented, obviously this method has been used in order to analyze the Lattice-Boltzmann method. So I'm telling you this because this method leads to has a little bit of different behavior, because it is really for deriving. You need a small parameter, and the small parameter in the Chapman-Enskog expansion is the Knudsen number, so it's the mean free path. Whereas in a numerical scheme, the small parameter is the discretization. Yeah, and this makes a difference, because in this Chapman-Enskog expansion, what you do is you have a fixed atomic distance, and then you scale up your problem and see what is the asymptote in when you make the system infinitely large. And by doing so, you will increase the Reynolds number, yeah, which is useful for physics, but it's not useful for our purpose here. This is now very, very briefly why we are not studying this, if you ever come around. So we say we do a discretization, of a fixed problem, and therefore our Reynolds number should keep constant. And what we also do is, I mean, what follows from this, because as we've just seen, the Reynolds number is the ratio between the Knudsen and the Mach number. This basically implies that Mach number scales like the Knudsen number. Yeah? So the Knudsen number and the Mach number are basically proportional to each other, because we said the Reynolds number is a constant and the Reynolds number is the ratio between the two. Yeah? So these are assumptions that go into what we are doing. So, and something that I also like to remind us, is time, the Navier-Stokes equation is a very useful thing, but it's not almighty. The Navier-Stokes equation falls apart at small length scales, where we go to the scales of the mean free path, obviously. Because then the Knudsen number being small is no longer the case. So there are a few examples where you can actually see, even in your very, very okay, so we may have large Knudsen numbers not only when we try to study re-entry of vehicles and near vacuum flows and so on. We may also have large Knudsen numbers in our daily life. So one example is if you have, say, a bucket. So this is not a beautiful bucket. And you have a tap here, and okay, so there's supposed to be water, and then you have a droplet coming into it. So what you would hope to see is you have, or what you kind of observe in the real world. You have this droplet falling to the surface to a water surface. And what you actually sometimes see is that this droplet bounces off. Yeah, this sometimes happens. But even if it bounces off, it will finally merge. And this is not according to the Navier-Stokes equation. Yeah, the Navier-Stokes equation does not allow this to happen. Yeah, so there's always a gap. I mean, this also, that the same thing is important for lubrication. Actually, my professor told us that in lubrication, it is physically impossible that if you have a gear and you have oil in this, there's a physically impossible that the metal touches. I mean, yeah, usually gears work, but it's not completely unheard of that something got stuck. Yeah, so actually they can touch, and they will touch. So this is a misunderstanding of the physics. Yeah, because if you start from Navier-Stokes equation and consider this is your physics, this is your base, then in lubrication you will get a thinner film, because you have no concept of discontinuity. Yeah, so this can go infinitely thin, which in reality it cannot, because atoms have finite size. Yeah, and if you come to the size of the atoms, you lose the assumption that Knudsen number is small, and the Navier-Stokes equation ends. That's here the point. So what would happen if you let a droplet fall into water? Then the Navier-Stokes equations predicts that the pressure in this gap rises to infinity before they merge. And so this will drive them apart. So the smaller the gap, the more the pressure, right? And so they will always stay apart. So I don't know whether this is a good, whether this is enough for convincing people that you should use the Boltzmann equation, especially if your Boltzmann equation is the lattice Boltzmann equation where we discretize only up to the order of the Navier-Stokes equation and such have the same problem. So no merging between the droplets and the water in the buckets. Now you know from experience that of course it is possible, and again this is only for L is much larger than lambda. And okay, just for completeness, I write this down. When the droplets gets closer to, no, I leave out sorry for my English. It's closer to the surface, lambda finally gets larger than L, and then Navier-Stokes equation invalid. So, do you have an idea what lambda roughly is for air? Einstein has calculated this from the viscosity of air. Give me a number. What is your guess? How many? Yeah, okay. So the order of nanometers is, you know, because I'm a MEMS engineer, so there was people who doing nanotechnology. So they then built devices that were 5,000 nanometers large. Okay, yeah, nanometers it's not in the lower nanometer, because the lower nanometer is I mean, you know what Armstrong is a tenth of a nanometer, and this is roughly the sizes that you have for atoms, right? So the path that they fly is larger than that, and say in air, I'm not completely sure whether Einstein calculated 100, but it's roughly of this order. Yeah, it's roughly 16 nanometers. Okay. So I mean, this gives you an idea on how small things can get before they you know, you have to think about different physics. This is of course related to one bar. Yeah. So if you go to Mount Elbrus 5.5, yeah, we take Mount Elbrus or Mount Kilimanjaro, because they have this height where we just have half the density. So there we would have 120 nanometers, and up then. Okay, so the next step, 1/4, would be 11 kilometers, which we don't have mountains of that size. Yeah. So Mount Elbrus and Mount Kilimanjaro are roughly on that 5.5. Yeah. So let's actually try to start our discretizations, and for this we return to the Navier-Stokes equations in terms of moments that we have written. So we have, so we are talking about the momentum. So I'll take the x momentum. So it's dt m100. Yeah. So this is the time derivative of the first moment. And on the other side we have, so this is basically what we did last time. We have the equilibrium, the spatial derivative of the equilibrium. We always count up with each x, we count up the moment here, this counter for x1 up. We are counting the one for y1 up, so this is 1, 1, 0 equilibrium, and then we'll have the set m101 equilibrium. Yeah, you understand how this works, right? Okay, so that's until here, this is the Euler equation, yeah? And then we get this dissipative part. In this lecture, we'll have not enough space in one line, so I have to write this in the next line. And, okay, here's already a simplification in this. You may have to go back and calculate that to see that this here is 1/3. The second derivative of now the equilibrium of the third order moment plus the ym120 equilibrium plus the m102 equilibrium. Okay, so basically it's a little bit more simplified that we ended up last time. We have taken the liberty of using the divergence, yeah, and so we basically had this thing here 3 times, and by rearranging we saw that 2 of them can be eliminated using the divergence, yeah, and this is basically left. So, I mean, this has nothing to do now with the discretization. This was the I mean, we got something of this order, yeah, as an arrow term when we start from the BGK equation. So, now the idea is now if we discretize up to these moments that we have, yeah, we can recover this equation, because this is the equation that we want to have. This is our Navier-Stokes. This is our Navier-Stokes equation. So the highest moments in Navier-Stokes is this M300, M120, and M102. So they are third order. Meaning, as I just said, approximating the Boltzmann transport equation up to third order moments is sufficient to solve the Navier-Stokes equation. If we want more, we have to invest more. Okay, now let's actually do this discrete velocity model in one dimension. So, main topic of today, and we start by introducing a very useful tool, which we call the characteristic diagram. So, this will be useful. So this is a way we describe in one-dimensional, in graphically, what we are doing, how we discretize. So characteristic diagram is we have to discretize space, which I call X, and we have to discretize time. And because this thing somehow originated from cellular automata, it now has become common to draw them the way cellular automata are drawn, space horizontally and time going downwards in positive direction. The bit we inherit this from cellular automata. So, and in this, we specify that we have so-called lattice nodes. These are these points here. And these lattice points, they all have the constant distance of delta x. And then they are kind of a cellular automaton which changes its state in time given a discrete time step delta t. So, but they also have so-called populations. We come to population in a minute. These are, say, kind of the number of particles or the probability. We use this interchangeable. The number of particles that go in a certain direction, or the probability for a single particle going in this direction. Yeah, and in here we use 3 different directions. So these particles could either go to the left, and then they will in the next time step they will have moved 1 delta x to the left, or they may go to the right, and they can also stay where they are. Yeah, so this gives us 3 velocities, and of course this happens on all these nodes simultaneously. So, and we have, so this here is delta x and this here is delta t, meaning that something that goes this way has a velocity c. Yeah? With c being delta x by delta t. And we call this the lattice velocity. The lattice velocity. Okay, then unfortunately, people have become very lazy in this context, and they often use something that they call lattice units. This may be a little bit confusing. So lazy, do we write lazy with 2 set or with 1 set? One lazy. Dyslectic. Lazily written in what we call lattice units, so that we just assume that delta x is equal to delta t is equal to 1. So, I mean, this is you know, I stopped teaching physics, but in physics you always have to teach the students that always write units everywhere, and then when you come to numerics, you have to teach them, remember, computers only deal with numbers. Yeah, no units here. Yeah, so the units are external. Yeah, so we already know what delta x, so we have to determine what delta x and delta t is. So they absolutely exist, but the computer doesn't care. It's moving one step right and left and is stepping over one time step, yeah? So, and therefore we often say, okay, forget this is length 1. Okay, now this thing here, this characteristic diagram will of course go on into the future, not here. And now on this we have to distinguish the different stages that this algorithm does. So we are here's at the time step, these populations are located on the nodes, and there they undergo a collision. Yeah, on the nodes they undergo a collision, and then next time they undergo a collision here. And in between them, they fly, or what we say, they stream. And then they stream here, they stream again. So what we have here in time is we have collision, and streaming. And we do this in this case for 3 discrete velocities. So it's our velocity, now I call this xi, is I times c, so c is delta x by delta t. This is the unit velocity in our lattice. So it's basically what I just said. And I, in that specific case, is taken from the set -1, 0, and 1, meaning 3 velocities. So CS. S is the streaming. So the populations. Okay, populations. Populations is, say, the number of particles in the same state. This is one interpretation, or the probability of a particle being in that state. Yeah, so basically the difference here, so the difference that it would make if the first one would be a number larger than 1, and the other one would be a number between 0 and 1. Yeah, and the difference is only how you scale it. But in Lattice Boltzmann, you can do it either way. Yeah? You can have either these large numbers, or you have numbers between 0 and 1. Both works the same way. It's just different interpretation. So, okay, I've not finished my sentence. So populations move with IC I delta x by delta t, with I being an integer. So we can have different discretizations, but we'll always have integer discretizations. Meaning that these populations, they hop from node to node. on a regular grid. So this is the lattice in lattice Boltzmann, yeah? So they have a velocity such that they end up on a node in the next time step. This is different from most other discretizations where you would have to interpolate something, yeah? So here there's no interpolation. Disadvantage, you have to have this specific connection between the velocities and the distance. Yeah, so that you always end up after one time step on a lattice node. So this is the one part of this, and the second part is the collision. So here what we have, the particles, or if you will, the populations, interact with each other on the nodes. So, of course, this implies only these particles that are in the same location, that are on the same node, they interact with each other. So they don't interact with particles or populations that are somewhere further away. Such models also exist for other reasons, but this is not classical lattice Boltzmann. So if you want to deal with liquids and you want to have free surfaces, then sometimes you also have far-reaching forces that you model in a different way. But classical lattice Boltzmann, only the operations are all local. So only these three populations that are associated with one node participate in the collision. So, question: how do we deal with moments of discrete, not moments, moments of discrete distributions? Okay, now we are only in one dimension. This is why I write M and only one index. And I know that is a bit annoying because this looks like Mach number. So this is M and index A, okay? So we get the integral from -infinity to infinity over our f and xi by the power of A, and integrate this over xi. So how is f actually looking? F is the sum over our discrete fi. So we sum over I, and they are discrete. So how do we express discreteness in a continuous field? We'll use the Dirac function. Yeah. So we'll write the Dirac function I times c minus xi. So this will, and then we integrate this over xi by the power of A and integrate this over xi. So now, as you hopefully know, the Dirac delta distribution is defined by its integral, saying that if the integral crosses the location where the argument of delta is 0, then this the value of this function here at this point will be is the integral, and when it's not crossing the value 0, the integral is 0. Yeah? So this is the definition of the Dirac delta. Now, and this makes it obvious that we actually get this here out of it. Yeah. So very simply, the integral becomes a sum. And by the way, I always like to point out that in reality, we also don't have a probability, but we have actually discrete molecules flying around in air. So you can, from discrete molecules, you see, by the same way, from discrete molecules, you still can calculate moments. You don't need a continuous function to calculate the moments. Yeah? So this is a bit like it is also in nature. So, having defined this, let us see what moments do we get. So first, the first moment that we get is the zero moment, yeah, when A is equal to 0. So it's Fi C times I, and this by the power of 0. Of course, this makes 1. That means we have F minus 1 plus F0 plus F1. So, okay, what is this strange thing here? We have 3 different directions, and of course you have the freedom to name them 1, 2, 3 in arbitrary order. So when you are European, you will probably start from left to right, and if you're Irani, you will probably read from, or for that matter, Israeli. Yeah, so they agree on one thing. Yeah, that they read from right to left. Yeah, so you can make this the way you want. This becomes very quickly very impractical in higher dimensions, even though it's usually done like this. This minus here is indicating that it's going in this one direction, in the negative direction. Yeah? And if we have more dimensions, we just add more indices. These things are called Miller indices. Miller indices. Or Miller index, yeah. So the way of writing lattice vectors like this. Have you ever heard about Miller indices? So you have heard, you have not heard. Daniel, have you heard? No. So Miller indices, I don't know how much responsibility I carry for using this in Lattice Boltzmann. I think somebody else also used this independently, but the idea here is, or let's say, for me this was very natural because I'm a semiconductor engineer. So we study crystals, lattices, natural lattices, and in the 19th century, this Mr. Miller from the UK already found a useful and simple and way of and unique way of describing lattices, yeah, crystal lattices. And we adapt. So for me, it was very, because I learned this for some other reason. For me, it was very intuitive to describe the lattices in Lattice Boltzmann also with this Miller index system. It is useful because it is absolutely unique. You once learn this, you can always describe all the different lattices. So in comparison to this, if you start now saying, okay, we start with 1, 2, 3, then you add more dimensions, then you have to somehow arrange them. And this leads to very strange, everybody has their own way of writing them down. And so you run very quickly in a lot of confusion. This is why I think we should always use Miller indices. Okay, so this is the zero moment is just the sum of all of them, right? Then the second is the first moment, Fi, Ci, and this is to the power of 1. So now we, you see, I is here is 0, so it will disappear. And what we are left with is minus F1 minus plus F1, and to be accurate, we have to multiply this by C. Yeah? And then we have the third guy is M2 is Fi Ci by the power of 2. Now, obviously, we do not distinguish between negative and positive anymore, but still, if I is 0, this will disappear. So we'll have F minus 1 plus F1 and this to the power C. Now, I just remember something which is important from an algebraic point of view. Because this is usually not true in mathematics, but we define this to be 1, right? Because up here, you see, we have also the case of 0 by the power of 0, right? So for us, 0 by the power of 0, for the purpose of this understanding, 0 by the power of 0 is 1, okay? So now we have 3 of them. Let's look at, okay, right, so we have 3 of them. However, we made a mistake. So we wanted to go to the third order moment, so we take 3 velocities, yeah? But now we make we discover that we actually made have a problem because we did not count that we had a 0 order moment. So our third order moment is already the first moment that we can calculate, right? So here, what we end up with is Fi Ci by the power of 3. And now what you observe is, because we have only 1, minus 1, 0, yeah, what we get here is F minus 1 plus 1, and this to C the third, to the third. And if we actually go one further, okay, should I write this? Fi Ci by the power of 4 is then F minus 1 plus F1 times C4, yeah? So what do we observe? I mean, very, very naturally, we have 3 discrete velocities. So from information theory, there cannot be more than 3 independent moments. And as a result, what you observe is that these guys are always the same, especially if you remember that C is actually 1, right? And also, these guys are always the same. And this being the same here is what we call moment aliasing. I always ask the students whether they prefer me to say aliasing or aliasing. I don't know, but okay, I say aliasing, yeah? Okay, so the reason, of course, is we have 3 discrete velocities . 3 discrete velocities means 3 independent moments. So, a little problem, because as we discussed, for our Navier-Stokes equation, up to third order moments are required. See, they are not independent. So these are M0, M1, M2, and M3. So there are 4 of them. So what do we know about them? M0 is the mass, or lazily we say sometimes the density. This is a conserved moment. Yeah, mass is conserved, density is not. But okay, it's a collision invariant. Okay, so mass m1. This is the momentum. Momentum is also conserved or collision invariant. And so, what is m2? Energy, correct. So, I watched Veritarium on YouTube and learned that actually energy is not conserved. It's a strange thing that I should learn this from YouTube, but okay, don't go into quantum physics now. Is energy conserved?
Classical physics, yes.
In classical physics. So what do we consider classical physics? Is it conserved in the Navier-Stokes equation? Does the Navier-Stokes equation conserve physics? No. Okay, no, it does not conserve physics. I mean, conserve energy.
Theoretically, yes.
Okay. Why do you say so?
Because all the forces, like if we sum up all the forces in the equation, it tends to 0. All the viscous forces, pressure forces, body forces, surface forces, and let's say also the weather.
They tend to 0. I mean, I'm not sure what you mean with tend to 0. I mean, if
it sums up to 0.
Well, they sum up to 0. Yeah, no, they don't. I mean, you have an acceleration, you have a time derivative on the left-hand side. I mean, if you have the Euler equation and you have a vortex, then this vortex will stay there forever, right? So if you have, or say, okay, one vortex is stupid because then you also have to talk about angular momentum. And suppose you have 2 vortices counter-rotating, or a ring. So now you have, so there is kinetic energy in this, right? So now you have friction. 2 counter-rotating vortices have 0, I mean, the same size. They have 0 momentum, right? So now you have friction, so they will die out. What happens to the energy?
Heat.
Heat, yes, they become heat. But is this part of the Navier-Stokes equation? No, just we have, there is this friction, and we stopped. Actually, third moments are called the heat flux. Yeah, so we stopped at the heat flux. Only equilibrium. Equilibrium means no heat flux. Yeah, so we would need to take more moments in order to see that there is energy conservation. So if we just look at the Navier-Stokes equation, it only conserves momentum. And energy is not conserved according to the Navier-Stokes equation. And this is the equation that we want to solve. So we have to concludes that energy is not conserved according to the Navier-Stokes equation, which is a good thing because you don't need to care about it. So you assume that energy disappears to somewhere, yeah? Which energy usually does. Energy dissipates, so it just goes away, yeah? I mean, it's not, it goes to another place where you don't see it, okay? And I mean, one thing that we did in our derivation last week was we assumed that that T was constant. So energy conservation implies that T is not constant. T has to rise. Temperature has to increase if you want to conserve energy, because you'll put this macroscopic kinetic energy into microscopic kinetic energy. Yeah, so it's also kinetic energy, but just at a different scale. I mean, it's also completely mysterious where you draw this boundary between, you know, the large scale and the small scale. Now somebody would potentially tell me there's the Kolmogorov scale. This is what above is rotation and below is heat. Yeah, okay, something of this sort. Yeah, it is a little bit fuzzy, I would say. Okay, so now what that means is that M2 is not conserved, and this is a good thing, because if M2 would be conserved, we would have nothing to change. Yeah, so the collision could not do anything. So the only thing that the collision can do here is changing M2. Now we want to use our BGK, and for this we have to find the discrete equilibrium. So obviously the conserved guys are simple because they are conserved, they stay the same, right? And we just define the zero order moment as the density rho, and we define the first order moment as the momentum rho u, okay, momentum density, yeah, and M2 equilibrium. So we have calculated this before. This was rho times CS, or can you tell me? CS square plus U square, right. Okay, now the problem is we actually also want to have this thing here, which we also already calculated, and what we found here is that this comes out as 3u rho CS square plus U square. Yeah, the 3 more or less comes from the permutations over which you see, this what you have here is M2, right? But you have 3 different ways by integrating to arrange M2 and multiply this with M1. Yeah? This is why we have, so you have 3 permutations there, you can do this. This is why we end up with a 3 euro CS. So basically because this is 3 times M1 equilibrium and M2 equilibrium, yeah, divided by M0. Because 3 ways of adding this. So anyway, this is what comes out. And this is a kind of our problem because we kind of need this, at least in equilibrium. We recognize we only need it up to equilibrium. However, now we have this problem of aliasing or aliasing. I see that M3 is equal to M1C squared. So what do we do? Other than hurrying up. I thought I don't have so much to write today. I'm just talking the entire time. So what can we do? We need to do 2 things here. Yeah, we have 2 problems. So this here is kind of supposed to be this here. Oh no, this here is this here. Yeah? M3 is this, but it's supposed to be this. So how do we get them closer? Well, for one thing is we can say that we are on an Eulerian grid, so we cannot entertain arbitrarily large velocities, yeah? Because we can only move one grid spacing per time step. So we are actually bound to having small velocities with regards to in the reference frame of our grid. So if we have small velocities in the reference frame of our grid, we now can assume that u to the cube should be small. So this is our assumption that we make. Velocity is small. So when velocity is small, we say that u cube goes to 0. And then this u times u square, this would be gone, right? Now then we have the second problem, that we have 3 times cs squared times u times rho, and what we are, okay, now I was pointing in the wrong place. It is of course this one, yeah? So this, yeah, sorry, when I said this should be this is of course wrong. This should be that, yeah? So it is rho times u, but it should be 3 times cs squared rho times u. So how can we deal with this? Well, we have to talk about what is actually cs squared. So cs squared is supposed to be Boltzmann constant times temperature divided by the mass of one particle. In physical units, and now in the units of our lattice, what we could do, I mean, one thing that would help us, if it just was the case, would be if cs squared is equal to c squared, so the lattice velocity divided by 3. Yeah? Suppose this was the case, then we would have, we didn't have this problem, and then we said that cs is, the square root of 1 over 3 in c. What does this mean? We have previously said we have a constant temperature. Yeah, we derived this under constant temperature. And what now we have to do is we just have to basically choose or scale the temperature such that the speed of sound is 1 over square root 3 of c. Yeah? Then our third moment has the right value in equilibrium. Clear? Okay, so this is about the moments, and now we would have to write all of this in terms of populations. So we have to translate between populations and moments. And here, for simplicity, I'm now using C is equal to 1. So this now will look like the things are not dimensionally consistent, yeah, because this means that the velocity is always given in delta x by delta t, which is 1, so we can add up numbers which don't look like dimensionally consistent, which is, of course, for physicists absolutely heretical, yeah? So we've seen that M0 is F minus 1 plus F0 plus F1. M1 is F1 minus F minus 1, and M2 is F1 plus F minus 1. So it's very simply, we solve this. This did not work. We just solved this to see that F1 is equal to M1 plus M2 divided by 2. F minus 1 is M2 minus M1 divided by 2. And F0 is M0 minus M2. Now we've seen what the equilibrium is. Equilibrium, so it's M0 equilibrium is rho, M1 equilibrium is rho u, and M2 equilibrium is, by our decision now, rho 1/3 plus u squared. Yeah? Such that we have the right value for the third order moment. Okay, so that can then be translated in FEQ1 being rho half 1/3 plus u square. F minus 1 looks very similar, obviously, just 1/3 minus u plus u square. And we have F0 equilibrium is rho 2/3 minus u square. So, and with this we can now build our BGK equation. Let's do this. Lattice BGK equation. Lattice BGK equation. So here we have again to distinguish between stream and collide. So what we do is we keep here one index and we write the position and the time in these brackets. Yeah? So we have the position x, and so there's some space in between here, and time t. So now streaming means we are doing a shift. We are shifting from the position x in the direction where the particle is moving to, or the population is moving to, and this is I times delta t. Times c. Okay, if you will say, okay, I times delta t times c. Yes, you're right. Okay, I write the c here. Yeah, so that this I times delta x actually. Yeah, and and here we go, of course, to the next time step. Yeah, and this is equal to the population in x and t after the collision. Yeah, so I write here an asterisk. This is what we have after the collision. So we have collide. So we generate an after collision population at the position x and t, which is the one that came before. And now you remember we had this Fi equilibrium. So they are now both at the collision positions minus f x and t, so some brackets. So now you remember we divided this by tau. Now I will make something different and write here an omega, which you could think for the time being as the inverse of tau. And one of the reasons, but this is not the main reason, but one of the reasons is in numerical methods we try to avoid to divide by things. Yeah. So if you have to divide by a constant, you should always take the inverse of the thing and multiply. That's much simpler. Yeah. So this up here again we call this is the streaming and this here is the collision. And we call this Fi asterisk the post collision, and Fi we call the pre-collision. And omega we call the collision frequency, so it's the inverse of a time, so it's a frequency. So now there is a mysterious way of understanding this. Or maybe in another way. So now we do streaming and collision, and it's a little bit mysterious whether we start with colliding or we start with streaming. And another thing that's mysterious is when we want to solve our Boltzmann equation, which is actually the right population or distribution that we are solving for. Is it the pre-collision or the post-collision? Because we have both of them. Yeah? So now it turns out, without going too much into the depths, actually both of these things, in reality both of these things kind of happen simultaneously. Yeah? While in numerics you split them and you do one after the other, while you should actually do both at the same time. And if you do this kind of splitting where you should do something simultaneously, but you do it one after the other, you of course get something that is called a splitting error. And this splitting error is usually of low order and is killing your method. So, how, and I mean, this property, I mean, looking at this, theoreticians up until until 2011, I believe, would simply say, okay, so this cannot, that's impossible to work. So in 2011, Paul Deller first, I mean, okay, I should say we know for much longer that this works just by doing the analysis and seeing that these error terms somehow disappear somewhere, yeah? But an elegant explanation why this happens was presented, I believe, 2011 by Paul Deller, using something that's, of course, not his idea, but that's used in mathematics that's called strung splitting. So strung is the guy who invented this. Yeah, so it does not has any other meaning. So strung splitting. Okay, how do we deal with the problem that we can either do CS, so we do streaming and collision, or we do collision and streaming, and they would come to different results. If we have an asymmetric splitting like this, we get errors of the order of 1 in time, which is regarded as being not good, say. So we get only first order accurate. Okay, I can make a claim here now. Because I had, back in this day, I didn't have any idea what strength splitting actually is. I've never heard about this. And my boss in Kyoto, yeah, who thought that this is all nonsense, he suggested to me that I use strength splitting in order to make this more accurate. And then he explained to me what strength splitting is, and then I thought about this and came back to him and said, we already do this in Lattice Boltzmann. There's no way I put this into Lattice Boltzmann because we're already doing this. And then he was very angry with me, you're so stupid, blah, 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 blah. And I stopped all of this, and then a few years later, I was amazed that Paul Della got, the big paper with saying you're doing strength splitting. Okay, now just funny story. It's not extremely mysterious. We do it in a little bit in a different way. Okay, problem is if you have something that's not symmetric, you get something that's usually first order accurate. If you think about it, if you have a symmetric time integrator, yeah, and you have some understanding of Taylor expansion, yeah, you know that if your time integrator is symmetric, it can only have even order errors. So the trick is to somehow make this symmetric. Yeah? Split this in a way that is symmetric. So time symmetric operators have even order of convergence. So I mean that this still can mean they are completely wrong, because zero order is also even, yeah. So they can be wrong, obviously. So there's no guarantee, but if they are not wrong, then they will be at least of second order convergence. So the problem is this is not symmetric. So how do we get this symmetric? We just write it in a different way. And now this is called splitting. What we do is we do a splitting of the streaming. Yeah. So what is the splitting of the streaming? Say we have Fi, X, and T, and so this is the pre-collision state, and from this I put everything on one side and equal it to 0, right? So I have a post, splitting or post streaming thing that I call FIS, and all what I do is I move the population not by one grid spacing. Okay, forget the C. But by half a grid spacing, and I do this for half a time step. And because I put everything on one side, I equal this to 0. Then I do my collision, Fi, getting the collision, x and t, minus Fi, x and t. So this is the difference between what we have, what we get out of this and the post-collision. And I call this now, okay, so compared to the above, I put this here on the other side, yeah? I put this on the other side and have omega Fi eq at the position x and time t minus Fi at x and t. So and now I did the streaming only half. So what I do next is I do another half streaming where I actually get this half streamed stuff off. So Fi after the streaming is now moving this by half. So here I'm pushing it 1/2 further, and here I'm pulling it 1/2 further, if you will. So t plus delta t half minus the post-collision thing, x and t, and this is equal to 0. So now what have we done now? We simply say that we do half of the streaming, then we do the collision, and then we do half of the streaming again, right? And then it is symmetric. Yeah, because this operation here is the same as this operation. And this here is in the middle, so now it's symmetric. And because it's symmetric, it has to have second order accuracy, or it fails. So we have this symmetric, so it's S 1/2, collision S 1/2, and then in the next time step we have S 1/2, and we have collision, and we have S 1/2 again, which means we have S 1/2 collision, and then we have a full streaming, obviously, yeah, and a collision and half a streaming again. So what do we observe? Now we can do this further and further and further. In between, here, we do not have to do anything different from what we actually do, yeah, because we are just streaming half the distance and streaming half the distance again. It's just at the beginning of the simulation and at the end of the simulation, we are missing half a streaming. Yeah? So even if this is an error of first order here, this error cannot grow. Yeah? It's just a constant offset. And you actually observe this constant offset if you don't take care about this in the simulations. With a constant offset, you have it once at the start of the simulation and at the end of the simulation, and everything in between is second order. And the fun part, so this is what my boss back then in Kyoto did not understand, is there is no change to the algorithm. So Lattice Boltzmann, we had Lattice Boltzmann long before we know that it's doing trunk splitting, but it's very useful to understand this and to analyze this. Maybe I should say that there was one difference in the way Paul Deller introduced this trunk splitting, because the only thing that you have to do is to make this thing here symmetric. And so his idea was, okay, he split up the collision, so he has half a collision, the streaming, and half a collision. And then because somehow he thought this, I asked him why don't you do this much simpler and say half a streaming and collision, half a streaming? And then he asked me, so what is half a streaming? And I mean this person is very, very intelligent. But anyway, what is half a streaming? I say half a streaming is streaming half the distance. And then yeah. Half collision is the average of a collision and doing nothing. Yeah, that's how he defined this. So now what we do instead is now we combine, as combined would then look like this. We say that fi x plus I delta t, and I add the c for you, divided by 2 t plus delta t half. So this is we forget about this fs, yeah? We combine the pre-collision with the post-collision, so they should be the same. I'll subtract them and set them to 0. X minus I delta t c divided by 2 t minus delta t half, and this is equal to 0, right? So we move the post-collision 1/2 distance, and we move the pre-collision 1/2 distance. So now this is when we write it down like this, instead of writing it down like the way we had it before, the analysis becomes much simpler. Yeah, and this is a good thing because we are already over 1.5 hours. Yeah, so let's do the analysis simpler, and we again use the Taylor expansion. At the points x and t. So x and t is at the nodes. Yeah, so it's at the node and at collision time. Yeah, so we call this equation 4.1, and I put the 0 on the left-hand side, and when I expand this at this position, I get fi x t minus fi asterisk, so after collision x and t, which, so this is this you can recognize as being the collision, and I think it should be minus the collision. Okay, I'll mistakes on my yeah, it should be minus the collision. Yeah, so because it's the post-collision minus, so okay, the other way around. But this is how it's written up here. Okay, let's continue with the Taylor expansion. I hope you are familiar. We go first in the direction of time. So we'll have time here. This is delta t half. This is the distance that we go, and we go dt. And now we'll we have here fi. Now this is all at x and t. I will stop writing x and t in future, because now obviously in the Taylor expansion this is all in this position. So we have plus f. Yeah, we go in direction delta t half, plus delta t half. Now on the other side, or here, we have minus fi after collision, and this goes in direction minus delta t. So because we have minus here and minus here, they will cancel out, and I get this fi asterisk plus x and t. Yeah? So now from here on, I will skip over the x and t here. Next thing is we go into the x direction. Okay, I've not written c here, so I write for you. I write c here, 1/2 dx. So what happens? The same thing happens, because we go here positive, here negative, but here is a minus, right? So exactly the same thing happens. Fi plus fi asterisk. So then we have we go to the second time derivative, so dt now, so this is dt square, and we go 1/2 square, and we go, so this 1/2 does not come from the Taylor expansion, it comes from the distance, right? But if you go the second derivative, we get 1/2 from the Taylor expansion, plus 1/2 square is apparently 1/8, okay? So then, now here we get difference, because now we go minus delta t square, so this will be minus here, yeah, minus this thing here, and then we also have delta t I and c square. This gives us also an 8 dxx. The same thing happens. And then we have the mixed term. So the mixed term has no. The mixed term does not has two factorial in front. Do you remember? So the mixed term has, because there are two directions. There's this 1 factorial times 1 factorial is 1. So it's just the delta x square that we have. So it will be 1/4, therefore, and we'll have a bit complicated. So it's delta t square, but it's only 1c now, and it is. Why do I have the I here by the film? I don't have the I here. I think this is nonsense. I don't have the I here, right. So and now we have the dx and t. Now this goes, let me see, yeah, this is the same thing, fi minus fi asterisk. Did I have any further mistakes? So let me stop at this order. Now we define something else very useful. And here again, I'm a very nasty guy, and I have to tell you, okay, I come from the Wild West time of Lattice Boltzmann. So everybody decides for themselves what they do. So for me, because strung splitting came much later, I made the connection like this. So I take an average, I define an average over pre and post collision, yeah, because we have to answer the question, so do we use pre-collision or post-collision? And I now suggest we use the average between pre and post-collision. So unfortunately, other people that have more followers than me on Instagram defined this in a different way. So they wanted that, so they came from the other direction, and they wanted that the final result uses f and not f bar. So for them, fi, so I mean, you will find papers. So in my papers, I'm always consistent in this format, but you will find other papers where they define the pre-collision with f bar and the average without overbar. Okay? So I'm sorry for this. There are different ways of writing this. So we'll now use this. Yeah? Because I find this natural. We do an average pre and post collision, so I put a bar there. Actually, I made the people agree that this kind of makes sense if there was not already another way to write it. Okay, anyway. So, why are we doing this? Yes, we do this because we assume that actually the average, so we make it symmetric, yeah? The previous was not symmetric, but we now have to replace this fi and this f and this f asterisk here. So, and what we can write probably looks a little bit stupid at first glance. Oh my God. Fi is equal to 2fi over bar minus fi after collision. Yeah. So it's just writing this in a different way. This can be written into fi 1/2 plus fi over bar minus fi asterisk half. Okay. This is supposed to make it more symmetric. The reason why we use this comes from this. When we look at our collision is fi asterisk minus fi is equal to omega fi equilibrium minus fi before collision, right? So now this can be rewritten as omega fi equilibrium. Now I replace this, what I have written up here, minus fi minus fi after collision divided by 2 minus fi average. Okay? So why are we doing this? We are doing this because we have this thing here and we have this thing here. So now next step is to bring this to the other side. So we have fi asterisk minus fi. So we have 1 from what is on the left-hand side. And now, okay, so there's the opposite sign. There's an omega here. And there is a 1/2, so because of the opposite sign, and we put it to the other side, it's twice minus, so it's omega 1/2, right? And this is equal to omega fi eq minus fi bar. So, why so? Now, if we assume that this fi bar, which is the symmetric thing, which does not exist in the simulation, but just the average between pre and post collision. Now this is exactly in the right format that we have in the original BGK equation, right? So we got this into the right format, but the collision operator kind of looks a little bit different because we still have this thing here in front. And this we want to get rid of, so we put it on the other side again. And we'll have then, if we put it to the other side again, we have 2 omega divided by omega minus 2 into fi equilibrium minus fi over bar. So this, you could say, is our equation 4.2. This is now kind of very important. We put this into our equation 4.1, where we have fi asterisk help me. I have a oh my God, I have a mistake here in the Okay, let me see whether we can. I have a mistake in the sign, so.
The last step, in the last step should be 2 minus omega. This here.
In the last step,
Yes, the equation 4.2.
yeah, 2 minus omega here. Okay, I have 2 minus omega. I guess that I may. Omega minus 2. So if it's omega, okay, so that would potentially help me. It's okay. So in order to have this, let me see whether we can correct this. So so suppose this here is correct. We are getting this from the further distance, and we are putting this further on. Okay. You know, it's too late for me to think properly. So usually I rely on my notes here, but my notes obviously have a mistake. So if I try to get this the same way that we had it before, and now I've exchanged these values here, this may help us. Let us see. So we have up there. What you see, we have 1/2 here, and here we have the sum of them. So we actually have the average. So we'll write that this is delta t dtfi plus I made another mistake. Sorry. We actually have, yes, sorry. We actually have an I here, and we also have an I there. And so we also have an I here. So you see, I prefer to have these lectures in the morning, but you guys wanted me to give lecture in the afternoon. So don't complain that I'm talking nonsense. I'm a morning guy. So we get I times delta t dx, and of course, yes, fi over bar plus delta t square divided by 8, and now we get this second derivative in time. Now let me briefly go back. So it's f minus f, it's fi minus fi asterisk, and going on with delta t. Okay, I forgot the c, but usually consider c to be 1. This is why I didn't write it. The xx, the same thing, fi minus fi asterisk, and also we got dt squared divided by 4 times I, and yes, c, but only one c, dxt, and this is the same thing, fi minus fi asterisk, and then we got terms of delta t to the cube.
Also the f asterisk minus fi, because we are moving it to the opposite side. The LHS.
No, we are moving here in the positive, and here we have minus. What do you mean? Did you mean something else?
Yeah, and exactly like we equated, like fi minus f asterisk was equal to 0. The LHS right now,
Okay, I don't. Where are we?
the LHS, the left hand side.
The left-hand side.
Yeah, that was meant to be on the right hand side, and that whole equation was equated to 0.
Oh, yes. You know, this explains my problem. Thank you. You see, I just need to. This actually means that my notes were correct. So since my notes were correct, unless this here, so because I thought that this was this incorrect. Because you made me here change the direction. So is this, I put 2 minus omega here, and then I put it on the other side. Yeah, looks like it's this way. Okay. So mistake. Okay. Yeah. Okay. We are almost done, but we have fi. So let us do the following observation. This is the collision. This is for changing in collision. And this is what we have here on the left-hand side. And we see that everything that we have on the right-hand side has at least one delta t in front of it. So this means that this here is of order delta t, right? Now, what does this imply? This implies that when I write order delta t square, and I have it here and here, a cube, I mean, then these things are also order delta t cube. Yeah, because they have delta t square in front. And these things here are delta t, order delta t. So they will all be absorbed into this. Yeah? And this is something that we get out of this strung splitting thing and shifting to half the time step. Yeah, so that they get easily removed. So let's put there 4.2 fi asterisk minus fi, which we identified now hopefully correctly, and it's written in a different way here. Okay, let's trust u, 2 minus omega, fi eq minus fi over bar, which is supposed to be delta t dt fi over bar plus dt. Okay, dtc times e dx fi over bar plus things of order delta t cube, right? So far, so good. So then we put this. So now what we want to have, I mean, this is already the equation that we want to have. We just have to rearrange it a little bit that it looks more like we want to have it. So we divide by delta t and bring this here into a little bit different form and put this on the left-hand side where it belongs. So we have dt fi over bar plus I. Now we don't get rid of the c. Dx, yeah, I mean, it's correct. I mean, c is I times c, right? So ic dx fi over bar, and now this can also hopefully be written as 1 over delta. Okay, so this is the right way to. It's usually written. Hopefully, no more mistakes. And this, because we divide it by delta t, goes into dt, is now dt squared. So, I mean, so what does this trunk splitting actually helps us? This trunk splitting, even though we have a direct, one-step integration like you do with Euler forward. Yeah, so usually you assume this is first order accurate, but due to this trunk splitting, we got this second order accurate. So it's as accurate as a low order Runge-Kutta scheme where you actually have to calculate one intermediate step. Yeah, so your intermediate step is kind of the streaming that you have to do. And other than that, we get here a little bit of modified thing in front of this collision operator. Now this is the BGK equation. Once we accept that we can write tau as 1 over omega minus 1/2 delta t. So this modification also comes from the trunk splitting. Yeah? And because this has been known since the 80s, so before we know about trunk splitting, this goes by another name, and this is by a Frenchman called Eon. He's written a paper. I've never been able to find this. I just know that this paper is actually in an astrological paper. Yeah. You go find it. Yeah, Eon, and it's written in French. Yeah, go find it and tell me. Yeah, so he discovered, I don't know by what means, that you have to make this shift. Yeah, and this shift. So originally they would say, so this method is first order accurate. It has this stupid error, but all that you have to do is redefine viscosity. Yeah, so you just set the parameter into a different value. So it's not 1 over omega, but it's 1 over omega minus 1/2, and then it's suddenly second order accurate. Yeah, that's the only thing that you have to change. Okay, yeah, sorry for a little bit confusion. I try to be more up to my mind next week. Yeah, I'll stop the recording now.